Hello everyone, and welcome again. So today we'll be studying the metals module of the Year 11 chemistry syllabus, and in particular we'll be talking about the mole in this set of lessons. So if you were to study chemistry, or if you were to start studying chemistry, this would be the place to start. This is probably one of the most important things that you'll learn as a Year 11 student, and if you don't learn this really well now, you'll have a hard time in Year 12 when you do more complicated problems regarding this particular concept. Okay, so listen in now and hopefully you'll be able to build up for Year 12 because this is very important for chemistry. So in today's lesson we'll talk about what the mole is exactly and what we actually do with it. And then in the next lesson we'll talk about how we calculate the mole as well as doing some actual problems where the mole is very useful. Okay. So here's sort of a primer on what the mole is, and it's this number here, 6.02 times 10 to the 23. It's a very big number, but we'll again go through each part and figure out where this number fits in to the greater part of chemistry. So first we'll have to define the mole, okay? Otherwise there's no real way that you can use it, of course. So the mole is the standard unit, and it's what chemists use to measure things, okay? So engineers and things use kilograms and meters. Physicists would use other things like charge. Biologists would use just numbers to count things, or maybe other units as well. But in chemistry, the mole is the very central unit, and that's how we describe chemical reactions. It's how we measure how much of a chemical we have. So we don't tend to use mass very frequently. And the reason why we don't use mass is because it's often not a good unit of measure in chemistry, because different chemicals have different molecular weights. Or for instance, if you were to look at, say, hydrogen as opposed to, say, oxygen, this thing only has one proton if you look at its atomic mass in the periodic table, whereas this thing has 8 protons and 8 neutrons. So this thing's 16 times bigger than this, yet they bond together to give you water, right? So just by looking at the masses of things won't tell you a lot, simply because they can just weigh a huge, a massively different amount. And so that's why chemists tend to avoid using mass straight away. They tend to work in moles first and then eventually work back to mass later at the end of the problem. So what is a mole exactly? And so how did they define it? Well, 1 mole is defined as the number of atoms in 12 grams of carbon-12. Okay, so there's a lot of 12s and numbers thrown around here, but we know what carbon is, and that's 6 in your periodic table, number 6. Which means it has 6 protons. Now carbon-12 just means that it has 12 nucleons, or 12 parts of its nucleus. So it has 6 protons, so carbon-12 must have 6 neutrons as well to make 12 parts of its nucleus. And so that's one type of carbon that we can find. And in 12 grams of that, we have that number from before, 6.022, or 6.02, times 10 to the 23. Now that's the number of atoms in 12 grams of carbon. Now that seems arbitrary, but most units in science are quite arbitrary. The meter was defined as 2 notches of the distance between 2 notches of metal at some stage. The kilogram was pretty arbitrarily defined as well. So it may seem arbitrarily defined, but it's what we do in science. So the number of atoms in 12 grams of carbon-12 is called Avogadro's number. So this particular number, 6.02 times 10 to the 23, is also called Avogadro's number. Okay? And he was one of the first people to study the mole, and that's why that number is named after him. Okay? So remember that it's 12 grams of carbon-12, and it's this number. But in general, all you have to do is remember this number, and that will tell you how many moles of a particular substance you have. So Avogadro's number is just 6.022, or O2, times 10 to the 23 particles. Okay. Now, what we can do with that is we can say, well, a mole can be used to describe any sort of object. Okay? As long as we have 6.02 times 10 to the 23 particles or objects, we have 1 mole of that object. Okay? So here's an example. 6.022 times 10 to the 23 cars on the roads or anywhere will give you 1 mole of cars. Okay? Similarly, 6.02 times 10 to the 23 humans will be 1 mole of humans. Okay? So we can use moles to count anything. So we can use it to count molecules as well. So carbon dioxide, we could have a mole of carbon dioxide if we had this many carbon dioxide molecules. So we just use it to count things. And you can also use moles to count components within molecules. Okay? So what does that mean? So let's take an example. We have CO2. If we have 1 molecule of CO2, so just one particle, so we have this, just this guy, you can see that there are 2 atoms of of oxygen for every 1 carbon atom. Okay? So you can see that if we had now multiplied that by 6.02 times 10 to the 23, so we get 1 mole of this now. So we've got 6.02 times 10 to the 23 of these carbon dioxide molecules. We got 1 mole of them. But that would mean that we have twice as many moles of oxygen, because remember, for every 1 carbon dioxide molecule, there are 2 oxygen atoms. So that means that we have 2 moles of oxygen in every 1 mole of carbon dioxide. Okay? So we're basically saying that, these numbers down the bottom will tell you a lot about how many moles of a particular thing we have in our chemical reaction. Now, using that 6.022 times 10 to the 23 is how we define the mole, but it's not very useful when we want to do calculations, because I don't go around measuring something and saying, well, look, I have 7.05 times 10 to the 24 atoms or particles of this particular substance. That's not easy to measure. So what we do is we want to measure weights. We want to weigh out a set amount of chemical, and then we want to be able to turn that into a mole somehow. Okay? So how we do that is we use a concept called the molecular weight or the molar weight. So molecular or molar, basically the same thing. There's not a big difference in what that means. But the molecular weight of a chemical is simply the amount 1 mole of that chemical weighs. Okay? So if I had 1 mole of any chemical, it would weigh a certain amount because there's a defined amount of particles. So hydrogen would weigh a certain amount if I had 1 mole of it. Carbon would weigh 12 grams if I had 1 mole of it. So that's the molecular weight. So again, for instance, 1 mole of just plain carbon, any sort of carbon, is 12.01. And the reason why it's 0.01 is because it's not all carbon 12 in a set of carbon. You'll have some other particles that have carbon 13, so there'll be more neutrons. Carbon 14, there'll be even more neutrons. So that throws out our measurement by a little bit. Now, where we find this data, the data for 1 mole of, or the molecular weight, or molar mass, or molar weight, we find that underneath the chemical name in the periodic table. So for instance, you might see, let's say carbon, it has 6, C, and then 12.01. Okay, so it has something like that. Maybe the word carbon will actually be here. And then underneath it will be a number, and that number is the molecular weight that I'm talking about. Okay? So that's good. So that allows us to transfer any units in mass, any measurements we make in mass, and it allows us to convert that into moles. And I'll explain how to do that in just a second. So just continuing the concept of molecular weight and molecular mass, if we have chemicals with more than 1 element, so like CO2 or H2O, stuff like that, the molecular weight is simply the sum of the molecular weight of its components. Okay, well, what does that mean? Oh, there's a lot of words there. So essentially what that means is each part of that chemical has a molecular weight. So hydrogen weighs X amount, carbon weighs X amount, or oxygen weighs X amount, or different amounts. So the molecular weight of the combined chemical is just the sum of each of those molecular weights of each part. So here's an example. CO2, we keep going back to CO2 because it's a nice easy one. So we have one carbon which has the molecular weight of 12.01. So you check your periodic table and that's what it is. And then it has two oxygens, so here's one molecular weight of oxygen and here's another. And so that is the molecular weight of carbon dioxide. 12.01 plus 16 plus 16, which is about 44.01. MM is what we use as molecular mass. That's our shorthand, okay? Molecular mass. And just check the units here. It's the grams per mole, okay? Because remembering that it's the amount of mass per mole of that substance, so it's always going to be grams per mole. That's our unit, okay? So calculating moles. Now we've learned about what a mole is. We've learned about molecular mass and molecular weight. But now how do we use that to calculate the mole? So we have a very, very simple equation. So for those who are studying 2-unit maths, 3-unit maths, you really have no excuse for not knowing this equation because it's very, very easy. So number of moles equals the mass of the sample divided by the molecular mass of the chemical. So we have a chemical, let's say sodium. We weigh out a certain amount of sodium, and that's the mass of the sample. And to work out the number of moles of that sample, in that sample, we just say, well, that mass of that sample divided by the molecular mass of the chemical in that sample. So the molecular mass of sodium is 22.99, I think, from memory. And so we just divide the mass by the molecular mass, and that's it. Okay? Very, very simple. And this is the standard form. This is the one you'll see in your syllabus. So N is the symbol we give for moles. Little m is the mass of the sample. So little m is always the mass of the sample. And sometimes it's just capital M, one capital M, but because I find that confusing sometimes, I use two capital M's for molar mass. Okay? So molar mass can be one capital M, but I like to use two just to avoid confusion. Okay? So then now that we know how to use that equation, well, what we're going to know is, well, how can that apply to our chemical equations? And don't worry if you don't fully understand the equation yet. In the next lesson, we'll do a lot of calculations with it, and you'll get plenty of experience using it. So when you balance chemical equations, the coefficients of the chemicals tell you the ratio of moles between those chemicals. Okay? Again, there's a lot of words there, but it will be clearer with the example. So let's take this equation, different equation to what we've been using before. So you've got calcium carbonate plus 2 hydrochloric acid molecules gives you calcium chloride plus CO2, carbon dioxide, and water. Okay? So you see here when we balance the equation, there's a 2 here. Don't worry about how we got this equation in the first place. Again, we'll get practice using this, but I just want to show you how we can use these equations. So when we balance this equation, we get a 2 here. And that 2 in front of the HCl tells you that for every 1 mole, because obviously if there's no number there, it's 1, just like in maths. If I wrote x plus 2, we know that there's a 1 here at the front. Okay? So similarly in chemistry, if there's no number, it just means 1. Okay? So the 2 here tells you that for every 1 calcium carbonate molecule that I use, we need 2 hydrochloric acid molecules. Or for every 1 mole of calcium carbonate that I have, we need 2 moles of hydrochloric acid for this reaction to finish, for you to have all of these used up. Okay? These coefficients, these things at the front, these numbers, are sometimes called the stoichiometric coefficients. So very big word, just means numbers at the front of the chemical reaction. Okay? So that basically sums up all the things that we need to know in terms of the basics of the moles. So we looked at how we define the mole, an Avogadro's number. So remember, the mole is 12 grams of carbon-12, the number of atoms in that, and that's 6.022 times 10 to the 23. And then we looked at how we can actually calculate it using molecular mass and using data that we actually have accessible to us. And then now we're looking at, and we finished up by looking at how moles relate to the chemical equation that we use in our reactions. Okay? So in the next lesson, we'll talk about actual problems and how to solve them. And so in that lesson, you'll get to use all these equations that I showed you. But we'll move on to the question segment, and we'll hopefully see how to apply some of the knowledge that we learned in this lesson. So first thing, we looked at this already, calcium carbonate. So calculate the molar mass of this substance. Okay, we want to know the molar mass. So here we looked up the molar masses of each of the parts. So let's see what all the parts are. There's calcium here, and then there's carbon here, and then there's oxygen here. So there's 3 parts: calcium, carbon, and 3 oxygens. As you can see, there's O3, so 3 oxygens. Okay. Now, remember that in order to work out the molar mass of this substance, we just add up all the molar masses of each part. So when I went and looked through my periodic table, I found that these are the molar masses of each element. Okay? So the molar mass of calcium carbonate is simply 40.08, the molar mass of calcium, plus 12.01, the molar mass of carbon, and plus 3 times the molar mass of oxygen, because there are 3 oxygens. Okay? So there's 3 times 16, rather than just 16. Okay? And then that gives you 100.09 grams per mole. Okay? And that's the mole. That's how we calculate the molar mass of something. If we wanted to go very complicated, we could say something like C8H18. And H is, okay, so, right? Now, all we had to do is just multiply 12.01 by 8, and this number by 18, add them together, and that's our molar mass, okay? So this concept is using very simple mathematics, just additions. The only tricky part is working out this data. We need to know where to get this data from, and that's from our periodic table, okay? So moving on. So we have calcium hydroxide is a substance called lime water. If there are 2 moles of calcium hydroxide, 2 moles in total, how many moles of OH minus ions are there? Okay. So you can see that there are 4 moles, because from this equation here, for every 1, so let's write it, CaOH2. Now for every 1 of these guys, there are 2 of these guys, right? So you can see that, because there's a 2 here. So if we looked at each molecule of calcium hydroxide, we'd notice that there'd be 2 hydroxide ions in them. Now if we have 2 moles of this, which is basically just saying we have 2 times 6.022 times 10 to the 23 molecules of this, then we'd have twice as many of these hydroxides. So if we had 2 moles, then we must have, of calcium hydroxide, we must have 4 moles of hydroxide ions. Okay? So that's how we calculate that. And you'll get lots and lots of practice in seeing these sort of things, because that's essentially what chemistry is built on. Now, if you don't understand it now, you can just keep practicing it, and eventually it will become second nature to you. That's something I can guarantee. So now we have this thing is burned in air. This is actually ethanol, or the alcohol that is in alcoholic beverages. So that's burned in air. The only products are water and carbon dioxide. So write the balanced equation for this reaction And if there are 3 moles of this substance, how many moles of CO2 are produced? So 3 moles of this ethanol, how many moles of CO2 are produced? Okay, fairly okay. So let's start by writing the equation. Okay, so we know that there's going to be this because it says we're burning it in air. And we know there's going to be oxygen because that's what burning means. Oh, I might move this across. And that goes to CO2 and H2O because that's what it says the products are. And that's what it tells us in the question. Now, all we have to do now is balance it. So let's do that. So first count the carbons on the left-hand side. So 1, 2, that's 2. And there's count them on the right-hand side, and there's 1. So to balance it, all I do is put a 2 here, because now there are 2 carbons, where there are 2 carbons here. So carbon is balanced. Now, what I want to do now is balance hydrogen, because hydrogen appears in this molecule, and only this molecule on the left-hand side. And hydrogen only appears in one molecule on the right-hand side. So that's how we balance things. Look for the chemicals that only appear once on each side, and it'll make your life much easier. So let's count how many hydrogens there are. 1, 2, 3, because there's 2 here. 4, 5, 6. So there's 6 hydrogens on the left-hand side, and there are 2 on the right-hand side. So how many times does 2 go into 6? Well, it goes in 3 times. So 3 times 2 is 6, and there's 6 here, so we're balanced. So we're okay. And lastly, we have oxygen. So we have 1 here. Don't forget this one, because a lot of people forget this one. So there's 1 here, and then there's 3 here. So 3 in total. There's 2 here. So 1, 2, 3. There's 3 on the left-hand side. So 2 oxygens here times 2 is 4, plus 3 times 1, which is 3. So there is 7 on the right-hand side, and 3 on the left-hand side. So maybe, how do we make 7 out of this? Well, we can multiply this by 3, and we get 6 plus 1 is 7. Okay? And that's how we balance the equation. So always start with the chemicals that only appear on one side of the equation in one molecule, and it'll be much faster. And so if we move, and there's our equation. Okay, so as I wrote it before. Okay, so hopefully you got that. Now, this question. If there are 3 moles of this, which is this, how many moles of CO2 are produced? Well, now we look at those stoichiometric coefficients that I mentioned earlier. So you can see there's a 2 here and a 1 here, because these are the 2 chemicals we're interested in. Now, for every 1 mole of this, we have how many moles of this? Well, we have 2 moles of carbon dioxide. So for every 1 mole of ethanol, we produce 2 moles of carbon dioxide. Okay? So now if we had 3 moles of ethanol, we would have 3 times 2 moles of carbon dioxide. We'd have twice that many, always twice as many as this. So we'd have 6 moles of carbon dioxide in total. Right? So from the equation, if there are 1 mole of ethanol, produces 2 moles of carbon dioxide. So if 3 moles of ethanol is consumed, then 6 moles of carbon dioxide will be produced. Okay? So that sort of wraps up today's lesson on the mole. So we looked at definitions mainly. We looked at what the mole is, what molecular mass or molar mass is, and how to calculate the mole using that equation. But we haven't really struck any new problems on it, so we'll definitely do that in the next lesson. And you'll see in the next lesson how to develop the answer from all this data that we're given. Okay? So I look forward to seeing you at our next lesson.